Welcome folks, and in today's video we will learn about quantum numbers, and we will be ably assisted by a cat called Irwin. Now, quantum numbers allow us to explain the behavior of atoms, the atoms that form, well, the world around us. And our understanding of the atom has changed quite a bit through the years. Thomson had envisaged electrons sprinkled around the atom. Bohr built on that by using a model where electrons exist at specific energy levels. And the electrons shown in green here can transition between the levels, but this would require a change in energy. Now, the quantum model sought to build on the idea of the specific levels of energy, but also solve some of the inadequacies of Bohr's model by viewing electrons as waves and using equations to graph the areas shown in red, yellow, and blue here, where atoms' electrons are likely to be found. These areas are called orbitals, and the Schrödinger equation used requires the use of quantum numbers to explain this electron distribution. The first quantum number is called the principal quantum number, and it is represented by the letter n. It describes how far an electron is from the nucleus, and it's connected to the Bohr concept of energy levels or shells. And so in this, the higher the n number, the more energy an electron has. So if we look at our electron wave, our little E wave here, it would start, the ones at the lowest energy level would start at n equals 1. And in order to get to n equals 2, it would need a bump of energy. And then the electrons at n equal 3 have a higher energy than those at n equal 2 or 1. So if we use our analogy of the atom as a cat hotel, and we bring good old Irwin into play here, the n value would represent the floor where our cat Irwin might be found. And the cats at the 4th level have more energy than those at the 2nd level. Maybe they need to climb the stairs as the elevators are out of order. Who knows? I also want to bring to your attention this notion that within the energy level, a big part of the quantum model was that within the energy levels, are these things called sublevels. Now, each energy level, the first energy level has one specific sublevel. The second energy level has 2, the third has 3, the fourth has 4, and so on. And these sublevels have specific letters attached to them, and they have different meanings. So that's what we're going to talk about with our next quantum number. The second quantum number is used to describe the shape of the sublevels that exist at each level. Now, it's often denoted by the letter L, and L can have any values of 0 to n minus 1. So 0 to n minus 1. So, for example, when n is equal to 2, the second energy level, then the electrons can be found in sublevel 0 or 1. So L can be 0 or 1. The 0 sublevel is at a lower energy level and is spherical in shape. So it's the one that's in green over here. We give it the symbol S, and it holds 2 electrons. The 1 sublevel is at a higher level, and it has a sort of a dumbbell shape, and it has the symbol P. This sublevel contains 3 orbitals, and each one of these orbitals contains an electron. So in total, the P sublevel has 6 electrons. Now, we don't see, there is more and more sublevels as you continue up the ends. We don't see the D sublevel here until n equals 3. So if we're to look at n equals 3, when n is equal to 3, the number of available sublevels is L0, 1, and 2. And so you can see that again, of course, there is the spherical L equals 0. There would be this one here, the third energy level. There's also a P sublevel at the end at n equals 3, so 3s and 3p. But on the third energy level, there's the D sublevel. So this D sublevel has the L equals 2. Now, to use our cat hotel analogy, the L number represents different room models, if you like, on the floor where cats are found. So if we look at Irwin here on the first floor, there might be a very simple room, which is in the S shape, and that only contains 2 cats. And then as we move up the floors, the configurations of rooms becomes more complex, and there's also more sub-levels at each floor. The next quantum number, shown by ML, describes how the orbital is oriented in space and how many orbitals there are per sublevel. As we move up the atom, the variety of sublevels where electrons can be found increases, and the orbitals in these increase too. So ML can have values from negative L to positive L, as shown here on screen. So if we just set up some examples here, just to put some meat on the bones, if you like, when L is equal to 0, then ML can only have one value, and that's 0. And remember back to when we talked about L is equal to 0, what we were talking about was this spherical shape. And that exists at every energy level, the first, the second, the third, and it's our S sublevel. Now, when we continue up in the second energy level, n equals 2, we're going to have L equals 0, but we're also going to have L equals 1. And remember we said L equals 1 is that P sublevel. And so if we look at our ML values here, it can go from negative 1, 0, and 1. So what that means in effect is that there are 3 orientations for that P sublevel. It can be oriented 3 different ways, and we'll have a look at that soon. And when L equals 2, so by the way, let's just go back and write these in. L equals 0 was S, L equals 1 was P, and L equals 2 was D. There are more, but we're just going to focus on the first 3 for now. There are much more energy sublevels as you continue up the different energy levels. But when L is equal to 2, so that D sublevel, well then the ML values actually increase. So the number of MLs, the number of orientations, or if you want to look at it this way, the number of orbitals is now 5. And so this D sublevel can hold up to 10 electrons because each one of the orbitals can hold 2 electrons. And the P orbital, which has 3, the P sublevel, which has 3 orbitals, negative 1, 0, and 1, each one of these holds 2 electrons. So it can have a maximum of 6 electrons. So I'm now going to show you an example of what I mean with the P orbital. If we use this as a model for the P orbital here, remember there's electrons in each one of these bulbs. It can be oriented in the X direction, the Z direction, or indeed the Y direction. So these are the different orientations in space, and it's a representation of the P model. Now, for to use our example of the analogy here, we got to go back to Irwin and his mates. Irwin can be at, cats can be at increasingly complex room configurations as they move up from the first to the second to the third. And for heavier elements, there would be cats in rooms that are oriented at different directions. But remember, there's 2 cats in the rooms, please, because they don't like to be alone, it seems. The final quantum number is called a spin quantum number. It is shown with a value ms, and the first three quantum numbers described how the electron is oriented in space and where it exists in space, where you're likely to find the electron in that orbital. The final quantum number describes how the electron spins. So if we're to use good old Irwin here, and we're to imagine a cat chasing its tail, then the electron is going to either spin clockwise or is going to spin anti-clockwise. I don't know whether cats chase their tails or whether that's just dogs. I don't think they do, but let's imagine that they do. The electrons definitely spin, and they create a temporary magnetic field, and the electrons can spin clockwise or anti-clockwise, and depending on what way they're spinning, they're given a value of -1/2 or +1/2. Now, the other important thing to say here is that no two electrons have the same 4 quantum numbers. So even if an electron, and we're just going to show one orbital here, let's say it is the 2px orbital, so it's the n equals 2, it's the sublevel p, and it's oriented in the x direction, and for that orbital it's going to have 2 electrons. And so if we just show them here with arrows, often we show them as pointed arrows, and this would be the first electron spinning this way, and this would be the second electron. And so even within the same orbital where the first 3 quantum number values are the same, these electrons would spin in opposite directions, as shown by the spin quantum number. So how can we put this all together, and can we, if given quantum numbers, how can we locate an element? Because essentially quantum numbers are almost like a postcode for locating an area where an element might, where an electron might exist within an element. So if we're given these quantum numbers, you may be asked, you know, where would the electron hang out, or even if these quantum numbers are valid for an electron in an atom. So let's have a look at this. If we have the n value is equal to 2, so we would start here with n equals 1. The nucleus is somewhere over here. And of course, at our n equals 1 value, the number of L options is just 0. And that's the spherical sublevel here. And it would only contain 2 electrons. So if you think of hydrogen and helium, their 2 electrons would exist at n equals 1, L equals 0. When we move up to n equals 2, we now have a couple of options. We have the spherical sublevel, and we also mentioned that we would have this p sublevel here. Now, in actual fact, the spherical sublevel is sort of in the middle, and then the different p options are oriented around that, and they're quite hard to show, but of course we have the x, the y, and the z. So we have a much more complex setup there, but if we look, we have the L value equals 0, and then our p sublevel is L equals 1. So within that, we're on the second energy level. We are on the p sublevel, and we said that the p sublevel actually has 3 different orbitals: the x, the y, and the z. And we're told that the ml value is 0. And remember, when we have our L set up, so the sublevel is equal to 1, the ml values can go from -1, 0 to 1. So if we're trying to locate this, and we're told that ml is equal to 0, that means we're talking about this middle orbital here. So that's where the electron, it's going to be at n equals 2. It's going to be the sublevel shape, which is a p sublevel, and then within that it's going to be in the middle orbital as shown by 0 here. And then within that itself, the final thing is the spin value is -1/2. So if we go ahead and we put in our 2 electrons in here, it would mean that specifically we're referring to this electron here. And also we can say that it can happen. So we can have a value of n equals 2, L equals 1, and ML equals 0. And then within these 2 electrons in this compartment, if you like, it's the one that's spinning, the first one that's spinning in that direction. So hopefully you found our model conversation useful and you have a better understanding of where quantum numbers are used as a model to understand the universe and the world around us. And they're also used as a way to locate where an electron might hang out in the atoms. And the final thing to say is that this is very important, because if we understand the structure of the atom by using quantum numbers to help our understanding, then we will be able to better understand how elements, compounds, and materials are going to act in certain scenarios.